All right. Hello and welcome to Online Lecture 7. So we were talking before about central tendency, the mean, the median, the mode, those sort of things. Well, today we're going to talk about frequency distributions because we want to understand not just the center of a distribution, but how things are laid out, how they're spread out, how they're distributed. Okay. So here is an example of why central tendency may not be enough. So suppose you were offered a internship that looked really good in Oklahoma City. And you might at first just look at a measure of central tendency, the mean, and say, look, the average temperature is 60.2 degrees. That sounds good to me. But then if you actually took into account some of the highs, as well as some of the lows, then you might suddenly think that, well, gets up to potentially up to beyond 110 degrees, gets down, way down there below 0 degrees into the negative, close to negative 20, maybe I don't really want to live in this non-temperate area. Okay, so maybe you do if that's not important to you, but the point is that just knowing the central tendency, just knowing the average is not enough to tell you all the information that you need. Okay. So let's start by considering frequency. Given a set of numbers, how can we make sense of them? Well, frequency is one way. It's the number of scores with a particular value. So if you survey 10 people and 3 people reported 2, then the frequency for 2 would be 3. Now, a frequency table is a table displaying the pattern of frequencies over different values, and we're going to talk about how to actually construct a frequency table. Okay, so here's going to be our steps for making a frequency table. Okay. Step 1. Make a list down the page of each possible value from lowest to highest. Now in our example today, we're going to be talking about people's ratings of happiness with where they are living. Okay, so this is a bunch of college students and we're asking them, how happy are you with where you're living? 0, not at all happy, to 10, extremely happy. Okay, so here's our scale that goes from 0 to 10. Now we're going to go one by one through the data values, making a tally mark for each next to its value on the list. So as you can see, 823, 129, 156, 944, etc., etc. These are all of our data values. And we went through each of them and made a tally when each one appeared. So 8 came up first, go to 8, make a tally mark. Then 2, make a tally mark, then 3, tally, 1, tally, 2, second tally, etc., etc. You go through the whole list like this. And if you did that, you would come up with this frequency tally. Okay. Notice that neither 0 nor 10 appeared in our data list, so we don't have anything near the 0 or the 10. Okay. Next step, just count how many times each value on the list was used. In other words, count the tallies. Okay, so 0 here, 2 here, 3 here, 4 here, 3, 3, 1, etc. So we're just getting our frequencies by counting up our tallies. Now, incidentally, it's tempting to skip this little tally step and just jump into the frequencies, but it's easy to make an error that way. It's easy to kind of miss a data point if you just go through and say, okay, how many zeros and go across, how many ones and go across. So I recommend the tally method. Okay. Then we're going to calculate the total frequency and then percentages for each value. Okay. So how do we do this step? First of all, we add up all our frequencies and we get 20. Then to get the percent, we would take, let's start with this value right here, the happiness rating 1, frequency of 2. We would take 2 divided by 20. We would get 0.10 multiplied by 100, because 0.10 is really our probability, multiplied by 100, and we would get 10. Multiplied by 100, and we would get 10. Same thing here. We have a frequency of 3. 3 divided by 20 gives us 0.15. 0.15 times 100, 15. Okay, so that's how we get these percentages. And then some people like to also include the relative frequency or probability for each value. Well, we already did that. That's the step we took before we even got to percentage, right? 2 divided by 20, 0.10. Multiplied by 100, 10. 3 divided by 20, 0.15. Multiplied by 100, 15. 4 divided by 20, same story, 0.20. Multiplied by 100, 20. Okay, so that's the other piece there. Okay. Now, a couple things to note here. The percentages should always add up to 100%, and the frequencies should always add up to 1. And if you remember, total probability cannot exceed 1, total percent cannot exceed 100. So it should equal those amounts, 1 and 100. If they don't add up, you know you have a problem there. It's a nice little double check for you. Okay. Now you can also have a frequency table for nominal variables, and you would follow the same 4 steps that you would for a numeric variable. The only difference is the values in which you are interested are names of categories rather than numbers. So as opposed to having something that would go from 0 to 10, we now have mental health symptoms post 9/11. And I'll tell you where this data actually comes from. It comes from World Trade Center Health Registry, which was voluntary for people who lived, worked, or went to school in the area of the World Trade Center disaster, or were involved in rescue and recovery efforts. And to enroll, people completed a confidential baseline survey. Okay, so based on the information they collected from these people who voluntarily decided to become part of this registry, they determined that 4,714 had symptoms of depression or anxiety. 137 had symptoms of post-traumatic stress disorder. 1,629 had symptoms of both. And having symptoms of neither is 4,908. Then you can get your total by adding these up, 11,388, and then you would just do the same game. 4714 divided by 11,388 times 100 gives me 41.4%. Once again, these should add to 100. Okay. One other kind of frequency table I do want to talk to you about is called a grouped or binned frequency table. It's a frequency table that uses intervals of values, the number of participants for each interval of values, okay? So let's consider bowling scores for a game that ranges between 0 and 300, right? So you can bowl 0 if you get all gutters, you can bowl 300 if you get all strikes. Okay, so as opposed to having a scale that goes all the way from 0, 1, 2, 3, all the way up to 300, that doesn't seem very helpful. What we might do is group or bin these together. Okay, so we might have 0 to 50, 51 to 100, 101 to 150, etc., until we get up to 300. So that can be something that is helpful to use if you have that kind of situation. Okay. So once we have our frequency table, we can actually make a histogram, which is a graph of the information on a frequency table. And the height of each bar is the frequency of each value in the frequency table. So now basically what we're going to do is we're going to rotate our frequency table 90 degrees. Let's take a look. Okay, here's our frequency table, right? This is what we had exactly before, no changes. Now we're going to put our values, as opposed to along the side, along the bottom, 0 to 10. Okay, had this been a grouped frequency table or a bin frequency table, the values would be the midpoints of the intervals. So if the interval was from 2 to 3, the value would be 2.5. Now you might be wondering, why do we do that? And honestly, I think the only reason is to keep this area not too crowded. So if we had those bowling scores of 0 to 50 and 51 to 100, it might get kind of crowded on the bottom. So I think, you know, you can use just the midpoint to keep it a little less crowded. Okay, so this is our happiness. These are our values. Then we're going to make a scale of frequencies along the left edge of the page. Now 0 will typically be at the bottom and the highest value will be at the top. Now we just make a bar for each value. Now remember, the value 0 had no frequency, so no bar. The value 1 had a frequency of 2, so it gets a bar right here. The value 2, excuse me, that was 1, that was 2. The value 3 had a frequency value of 4, so it gets the bar right there. And so on and so forth throughout the whole histogram. Notice the bars in a histogram touch. Notice the bars in a histogram touch. So that actually is a feature of a histogram. Okay. Now what happened here? What happened here? What did I do here? I didn't change anything along the bottom, but if you notice, I changed this scale. It used to go from 0 to 4. Now it goes from 0 to 100. Quite the difference. It all looks smushed down. If you look here, it looks like there's some really important or interesting differences across the different frequencies. Here, it looks like there's no differences. So perhaps this is not the best way to draw a histogram if the values only range from 0 to 4. Perhaps this is a false representation. Okay. Let's look at one more example of a false representation or a distorted histogram. Now this one is probably the one that's kind of the just right, you know? The scale along here kind of matches the scale along here. Sorry, I should say the scale along the bottom along stress rating matches the scale along frequency in that upper left-hand diagram. Whereas if we go to the bottom left-hand diagram, we notice that it all kind of looks scrunched together and the differences become kind of flattened out. And if you look at the diagram on the right, where we stretched out that y-axis, that frequency axis, it kind of exaggerates differences between the frequencies, between the different values and their frequencies. Okay, so good rule of thumb, although it's not perfect, but good rule of thumb is if you keep your axes similarly scaled, you should be in good shape. Okay, all right. There's a bit of common sense or common agreement that goes into this as well. So, but I think we can pretty much agree the upper left is probably the histogram we like the most. Okay. Okay, so now that we have a sense for how to make a frequency table and how to make a histogram, we can talk a little bit more about frequency distributions. So as we talk about these different distributions, I want you to imagine the histogram and how it would actually look. Okay, so frequency distribution shows the pattern of frequencies over the various values or how the frequencies are spread out. So a unimodal distribution has a histogram with one very high area. Let's say I gave you, just for fun, a six-sided die, but the die only had on it twos and a single one, a single six, but four twos. What do you think would happen if you threw that die 1,000 times? What number would come up the most? I suspect you would say 2, right? And so when you can imagine that histogram, it's going to have one very high point at 2 and low points at 1 and 6. Bimodal distribution. This is a distribution with two fairly equal high points. So now we have a die with two twos, two threes, a 1, and a 6. Now both the 2s and the 3s will come up rather high, and the 1s and 6 will be less so. Multimodal is a distribution with 2 or more high points. Now that's interesting because we just said bimodal is 2, right? Multimodal is 2 or more, which means that bimodal is a type of multimodal. So if something I say is bimodal, it has 2 high points, that immediately means it's multimodal as well. But a multimodal could have 3 high points, 4 high points, etc., etc. Okay. And finally, a rectangular distribution is when all values have approximately the same frequency. This is our standard die, numbered 1 to 6. Throw it 1,000 times. What are you going to get? Pretty even distribution of 1s through 6s. So now, to help us out, let's look at some pictures. At the top, you see a unimodal distribution. All right, you see that, hopefully that one high point near the center. In the second diagram, you see an approximately bimodal distribution with 2 high points. It almost has a little bit of a third high point wanting to happen, but it really doesn't quite happen. So we would just call this bimodal because of the 2 high points. Okay. Remember, we could also call this multimodal because 2 or more high points is multimodal. And then finally, down at the bottom, we have a rectangular distribution, which is approximately rectangular in this case. The reason I really like these diagrams actually and show you these images is because they're not perfect. And when you're working with data, it's rarely perfect. And you're probably going to get images like this rather than something perfect like this. Now, this is our normal curve. And it is quite perfect. And we are going to be talking about the normal curve a whole bunch going forward because we're going to rely on this normal curve. We're going to count on it. We're going to assume that a lot of our variables have this distribution look like this if I were to actually draw a histogram. Okay, so let's talk more about this normal curve. It's bell-shaped. Okay, think of an old-fashioned bell. It's unimodal, notice the one high point, and it's symmetrical, right? So bell-shaped, unimodal in the one high point, and symmetrical, which means if I took it and fold it in half, the two sides would equal each other. Two sides would line up. Okay. So what kinds of different variables take on a normal curve distribution? Well, there's a whole bunch, but let's just talk about a few. People's heights. Heights tends to take on a normal distribution. Test scores. We didn't actually get to talk about this on the first day, but if you've ever heard of curving a grade or the distribution of grades, it typically follows a normal curve. Sizes of snowflakes follow a normal curve, and IQ scores tend to follow a normal curve. So all these different things that happen naturally in society happen to follow this normal curve distribution, and many, many others, as we'll continue to talk about in the course. Okay. So a normal curve is a symmetrical distribution. You have approximately the same number of values on both sides of the distribution. Now, if you don't have a symmetrical distribution, perhaps you have a skewed distribution. Now, a skewed distribution are distributions where the scores pile up on one side of the middle, whereas on the other side of the middle, the scores are spread out. Okay, so let's take a look at this. In A, we have an approximately normal distribution, approximately symmetrical, I should say. In B, we are skewed to the right. It's a positive skew. Now, this gets a little confusing. Positive skew and negative skew all depends on where the tail is. And that's a little counterintuitive. So whenever you're talking about the skewness of distributions, follow the tail. And this is what I mean by the tail, right? If you imagine this to be an animal, this might be the tail here, okay? And over here in C, we have a skewed to the left or negatively skewed distribution. And again, follow the tail. Notice the tail going out to the left here. That's negatively skewed. Okay, so always follow the tail to figure out whether it's positive or negative. Okay. Okay. Something else we could have happen with distributions are floor effects and ceiling effects. A floor effect is when scores pile toward the lower end of the distribution because it's not possible to have a lower score. An example of this might be number of children. Now, of course, there are exceptions to the rule, but most people have 0 children, 1 child, 2 children, 3 children maybe, 4, 5, getting kind of rare, 6, 7, 8, really rare, right? So things are kind of piling up toward the lower end of the distribution. A ceiling effect are when scores pile up toward the upper end or the higher end of the distribution because it's not possible to have a higher score, such as scores on a very easy statistics test. Okay, so if you had a very, very easy test, there was only one question on it, and you just knew it, and it was really easy, and all your classmates felt the same way, then what would you find? Most people would probably get 100 or 95 or 90, something very, very I guess let's say it has more than one question because otherwise we can't have any distribution there. But most people would score very, very high and we'd have a ceiling effect. Okay. So let's take a look at these. Number of children. See how it's got this floor effect right here? All the zeros, ones, and then we slowly decrease our frequency as we get larger in terms of number of children. Whereas we have the opposite, the ceiling effect here with percentage of correct answers. Most people getting 100, less getting 90, drop at 80, etc. And if you are thinking that this reminds me of skew, you're absolutely right. You can have a positively skewed distribution due to a floor effect. Notice that tail going to the right. And a negatively skewed distribution due to a ceiling effect. Notice that tail going to the left. Okay, so yes, there is a relationship between skew and floor and ceiling effects. Okay. Another kind of distinction we can make is between heavy-tailed and light-tailed distributions. Heavy-tailed is when there are many scores in the tails and the tails are thick. Light-tailed is when there are few scores in the tails and the tails are thin. So we'll compare this, we'll look at some pictures in just a moment and compare this to our perfect, our beautiful normal curve, which neither has heavy nor light tails typically. And let's take a look at how this looks. So here's an example in A of normal curve. B is a heavy-tailed. So here in the dashed line is our normal curve again. Okay, and in the solid line is a heavy tail distribution. And again, look at those tails, look out toward the end. That's where the tails are at the end. That's where tails usually are at the end, right? So if you look out toward the end, toward those tails on the left and right side, you'll notice there's a fair amount of distance between the tail and the axis and the straight line. That's a heavy-tailed. Whereas if we look at C, once again, in the dashed line, we see our normal curve, and in the solid line, we see a very, very light-tailed distribution. Okay, and you'll notice there's almost no tail here, right? It just kind of drops immediately. It doesn't kind of go out to the right or left. Okay. And another name for looking at the heavier or light-tailedness of a distribution is kurtosis. So we can talk about the level of kurtosis of a distribution, whether it's heavy-tailed or light-tailed. Okay. There's our normal curve once again. I want to show you that one more time so that it kind of stays with you guys. Because like I said, it's going to be a very important curve going forward. Okay, remember it's bell-shaped, unimodal, and symmetrical. Okay, and that's it for this lecture. So stay tuned for the next one about variability.